Okay, thank you very much for this invitation to come and tell you about gravitational waves. And I'm going to tell you about a particular aspect of gravitational waves called gravitational wave memory. And I want to start with a few acknowledgments. So my work on gravitational wave memory is mostly in collaboration with Professor Lydia Bieri in the University of Michigan Math Department. And some of it's also in collaboration with Bob Wald, Alex Talish, S.T. Yao, Nico Yunus, Istvan Roch, Stefan Hollins, and Akihiko Ishibashi. And in addition, because my work is funded by the National Science Foundation, that means that my research is also supported by the US taxpayers, in other words, all of you. So I want to acknowledge and thank you for your help in doing my research. So this is an outline of what we're going to be doing today in this talk. So I'm going to start with a couple of quick demonstrations about radio waves and about laser interferometers. And the reason for this is that it turns out that gravitational waves are a lot like radio waves. And we're a lot more familiar with radio waves than we are with gravitational waves. And so what that means is that by remembering how radio waves work and thinking in analogy, we'll have a better chance of understanding how gravitational waves work. Now, it turns out that gravitational waves are very weak. And so in order to have a chance of detecting them, we need very large masses moving very fast. And this only happens in the case where the masses are either neutron stars or black holes. So I'm going to, after the demonstrations, tell you, or perhaps since many of you are regulars here, remind you about the properties of neutron stars and black holes. And then I will talk about the property of gravitational waves. Once I've done all that, I will have set the stage for the main topic of this talk, which is gravitational wave memory. Now, this is something that you don't often hear about in a talk on gravitational waves, because usually what people tell you is that gravitational waves stretch and squeeze space, and so you might think that after the gravitational wave has gone, that space has returned back to its old unstretched, unsqueezed state. But it turns out that that's not true. There is a tiny residual stretch and squeeze of space that's left even after the gravitational wave has completely passed by. And that residual stretch and squeeze is called gravitational wave memory. So I'll say a little bit about that, and then I will talk about, again, using radio waves as an analog, an electromagnetic analog of gravitational wave memory, which will help us understand this phenomenon a little bit better. And I'll also explain about tidal force and the curvature of space and time, which will also help us to understand gravitational wave memory better. Finally, I will then talk about how gravitational wave memory works in the expanding universe. And then I'll talk about the prospects for detecting gravitational wave memory. Because even though, as Fred reminded you, gravitational waves have been detected, gravitational wave memory has not yet been detected, but we expect it to be detected sometime in the next few years. And then finally, I'll conclude. Okay, so that's the plan of the talk. So now, let me get to the demonstrations. So one of the keys to understanding gravitational waves is to remember that they're like radio waves. And for that, it's going to be handy to remember what radio waves are like. So I have here a nice simple demonstration. So the idea, even though we're used to dealing with radio waves all the time, we sometimes don't remember just exactly how simple they are. So this apparatus basically consists of a couple of wires here, and then an oscillator which will drive an electric current back and forth in this wire millions of times a second. And when it does that, it makes electric and magnetic fields, and those electric and magnetic fields move out in all directions. And when they hit these wires, they will drive an electric current up and down in these wires, and that will light this little light bulb. And I'm going to turn it this way for reasons that will become clear in a minute. So you might wonder, okay, well, what's going on here? You know, here I promised you that the light bulb would light, and it's not. And the reason is that because the transmitting antenna is horizontal, that means that the electric field that it's generating is in the horizontal direction. So if I carefully keep the antenna in the vertical direction, as I learn to do so as not to blow out the bulb, then there will be no lighting of the bulb. But as I turn the receiving antenna in the horizontal direction, the light bulb lights, right? So I notice that as long as I'm aligned with the electric field, I get the light bulb to light, and the closer I am to the transmitting antenna, the brighter the light bulb is. If I move further away from the transmitting antenna, the light bulb is dim. Okay, so the basic idea then is that all we do is we move electrons back and forth in the transmitting antenna. That makes electric field. The electric field moves out. It hits this, and it makes the electrons in the receiving antenna move back and forth, and that can be used to light a light bulb. Okay, so gravitational waves, despite all of this stuff about curved space-time and Einstein's field equations and things like that, are not really all that much more complicated. Masses have a gravitational field, and when you move masses, they make a gravitational field that propagates outward, and as that gravitational field comes to you, it will move any mass it comes in contact with. So just like radio waves will move electric charges, gravitational waves are made by moving masses and will move any mass they hit. Okay, so that sounds really simple. So it sounds like I should be able to just have an apparatus that looks like this, where I go ahead and have a bunch of moving masses, maybe a centrifuge or something, and over here I have a detector and it will make those masses jiggle. Unfortunately, gravitational waves are much, much weaker than electromagnetic waves. And so what that means is that it's a very delicate kind of measurement to find the changes that a gravitational wave makes. So what you need is an enormous source of gravitational waves, really big masses moving at really high speeds. But you also need a very delicate apparatus. When the gravitational wave finally comes to your detector, what it's going to do is to slightly stretch space in one direction and squeeze it in the other direction. And those stretches and squeezes are going to be very, very small. So what you need is something that can detect those tiny changes in length induced by the gravitational wave. Well, it turns out that there is such an apparatus, and it actually figured prominently in the history of relativity, and that apparatus is an interferometer. So let's see. Let me go ahead and turn this one on. Let's see. Wait a second. Oh, this one, right, of course. Okay, thank you. Okay, so the idea of this apparatus is that you have a laser beam, and what it does is to go into this mirror, and when it does that, it's split in two. So half of the beam goes to this mirror, bounces back. The other half of the beam goes to this mirror and bounces back. And then those two beams interfere in this screen over here. Now, the wavelength of light is very small. And if you change the length by just a wavelength of light, that will change the interference pattern from dark to light. And so in fact, if I just do a small disturbance, like, for example, changing the pressure in a little air chamber between the two mirrors, or even just pressing on the apparatus, you can see that the interference pattern will change. So this is a very sensitive measure of length. And in fact, it has to be, because in the apparatus that detects gravitational waves, the change in length is really going to be a small fraction of the wavelength of light, and so you have to see not a change in fringe from light to dark, but a change in fringe from a particular lightness to a slightly different lightness. It's also the case that the amount that gravitational waves change the length of something is proportional to the length that it had to begin with. So you get a bigger signal by having a much bigger interferometer. So this interferometer has a distance between the laser and the mirror of just a few inches, whereas the LIGO interferometer that detected the gravitational waves, there the length of each of the arms is about 4 kilometers, and I'll show you a picture of that later. So the measurement is devilishly tricky because there aren't very many sources that are strong enough to generate the gravitational waves. You need a gigantic laser interferometer, and you need to look for a very delicate change in the length. But the conceptual idea is not that hard. Just as electric charges make radio waves, and those radio waves move charges, so all that's going on with gravitational waves is moving masses make gravitational waves, and those gravitational waves move masses. And so in this case, it's the neutron stars and black holes that make the gravitational wave. The wave travels to the LIGO interferometer, and it jiggles the mirrors a little bit, and that jiggling in the mirror is what they detect. Okay, so that's it for the demonstrations. Now I want to move on and tell you a little bit about neutron stars and black holes, which are the things that are the sources of these gravitational waves. So the basic idea is that stars are powered by nuclear fusion. And nuclear fusion starts with hydrogen, builds the hydrogen up into helium, builds the helium up into carbon and then oxygen. Small stars like our sun will basically stop there. They'll never get beyond carbon and oxygen, and they will become stars called white dwarfs. But large stars keep on with their nuclear fusion, and they make heavier and heavier elements until finally they come to iron. Now, iron is the heaviest element from which you can get energy out of fusion. There are certainly heavier elements than iron, and those heavier elements can be produced by nuclear fusion, but you won't get any more energy out of them. And so what that means is that once a star has built up a core of iron, that core no longer is generating energy to heat it up to maintain pressure that keeps the thing from collapsing. And once the iron core gets large enough, that iron core itself will collapse, and the whole rest of the star will explode in a gigantic explosion called a supernova, and then what's left in the center is either a neutron star or a black hole. Okay, so now, having told you that, let me go over that in a little bit more detail. Okay, so this is a crude diagram of a star, and this circle in the middle is going to be some particular layer of gas inside the star. These inward-pointing arrows represent the force of the star's own gravity that's trying to pull it in and make it collapse. And the outward-pointing arrows are the star's pressure, which is trying to push it apart and make it explode. And stars are in equilibrium between the inward force of gravity and the outward force of pressure. However, as the star uses up more and more of its fuel, the kinds of pressure that it can generate changes. And so there's always the possibility that gravity might win in the end and that the star might collapse. All right, so what are the sources of pressure? How does the star stave off gravity? Well, one source is fairly easy to understand. The star is made of gas, and hot gas has pressure, and the hotter the gas, the more the pressure. So as long as the star can keep itself hot, then it can stave off collapse. It can withstand its own gravity. But even without heat, there is a different kind of pressure called electron degeneracy pressure. And this is just caused by the fact that electrons repel each other, not due to their electric charge, but just because of a funny quantum mechanical property that says that two electrons don't want to be in the same place. So even after our sun has used up all its fuel, it nonetheless will not collapse because this electron degeneracy pressure will keep it from doing so. However, it was found many, many years ago by Chandrasekhar that a core of a star can only be held up by this electron degeneracy pressure if it's less than 1.4 solar masses. So that's fine for our sun, right? Our sun is 1 solar mass, so it will not have any trouble holding itself up with electron degeneracy pressure. But that's not so good for the iron cores of these big stars. Right? So the big stars will build up more and more iron in their core. The iron has no fusion of its own to keep it up, and electron degeneracy pressure will only work until the iron core gets to about 1.4 solar masses. And at that point, something catastrophic happens. Okay, so what happens when the iron core gets to about the Chandrasekhar limit? Well, it turns out, so we remember, right, that atoms are made of protons, neutrons, and electrons. And what will happen is that the electrons and the protons will combine to make neutrons and neutrinos. So now you have this huge core of iron that suddenly becomes a huge core of neutrons. And you have these neutrinos that have been released by this core. So the neutron core will collapse until it becomes about the size of a small city, and the neutrinos will stream out and cause the rest of the star to explode. This gigantic explosion of the star is called a supernova, and the core of neutrons at the center is called a neutron star. So this is about 1.4 times the mass of the sun and about the size of a small city. However, for very, very massive stars, enough of the rest of the star will fall back that the neutron star and all the rest of this matter will not be able to hold itself up against gravity, and then it will collapse completely. So what does it mean for it to collapse completely? Well, what it means is that all of the matter gets smaller and smaller, until finally its gravitational field becomes so strong that even light can't escape from it. Now, because nothing can travel faster than light, if you have a gravitational field that's so strong even light can't escape, that means that the matter is going to continue to collapse, get smaller and smaller, and finally it will be a point in the center, a point of infinite density and infinite curvature called a space-time singularity. But we won't see any of that. And the reason is that if you have a gravitational field that's so strong even light can't escape, then nothing of the stuff that happens inside that will ever get out to you. You won't know anything about that. So for our purposes, we think of just this imaginary place where the gravitational field just becomes strong enough to pull light in. And we call that the event horizon. And everything inside the event horizon is something that we'll never find out about. So for our purposes, we can just think of this as just an event horizon. and that object is called a black hole. So we ignore all the stuff that goes on inside the black hole because we don't get to see it, and we just say, okay, well, for some reason, there's this enormously massive object here, and it's pulling everything into it, and we call that a black hole. Okay, so now we know how you get these enormously compact objects. So from the gravitational collapse of very massive stars, you make some neutron stars, you make some black holes. Now, as Professor Adams was reminding me, most massive stars are in binary systems. That is, two stars in orbit around each other held by their own gravitational field. So in particular, that means that if you have two of these massive stars, you can make a system that has two neutron stars in orbit around each other, or two black holes in orbit around each other, or one neutron star and one black hole. Now, what happens when you have a system like that? Well, the gravitational field of each of these is pulling on the other, and so they orbit around each other like this. But because they're moving masses, that means they're making gravitational waves. And some of the energy in that system gets lost in the form of gravitational waves. And so these things will get closer to each other. And as they're closer to each other, they move faster and faster, make more and more gravitational waves, move faster and faster, and so on, until finally they collide and form a black hole, and in the process emit more gravitational waves. Okay, so now I'm going to attempt to show you a movie that's a simulation of this process. So let's see if we can get this movie to run. So basically, the two objects in the center are two black holes of different sizes, and these ripples are going to be the strength of the gravitational waves that's emitted. And this thing on the bottom will tell the story of the signal that's emitted. So in other words, you start with things at fairly low amplitude and low frequency, and as the black holes get closer and closer to each other, things will ramp up to higher amplitude and higher frequency until finally they collide and give a burst of gravitational waves of more frequency. All right, so let me see if I can get this thing to run. Hang on one second. Okay, so now it's going to zoom in so you can see them closer to each other. So there they are going around each other, getting closer and closer. The gravitational wave signal is getting faster and faster and also stronger and stronger. Okay, and now we're zoomed in even more. They're going to get closer and closer to each other and finally merge. And now they've merged and they're sending out that last set of ripples of gravitational waves. Okay, so people have successfully done such simulations since 2005, but the difference is that now we know that these things are real because gravitational waves have been detected. So this is a picture of the apparatus that did the detection. In principle, it's not all that much more complicated than this laser interferometer right here, although in practice there are a whole bunch of extra bells and whistles that they put on to make this thing work as well as it does. So there are actually two laser interferometers, and the reason is that any single apparatus can always have some noise in it that you might accidentally mistake for a signal. But when you have two of them, if the two of them simultaneously detect something, then you know you have something real. So these are two laser interferometers, not much different from this one over here. But their arms are 4 kilometers long. So over here, what you have is a laser and a beam splitter that will split the laser beam into 2 pieces. And then you have 2 vacuum pipes 4 kilometers long. So one laser beam goes down this pipe and hits a mirror 4 kilometers away at the end and bounces back. The other half of the laser beam goes down this pipe, hits a mirror at the end, bounces back, and then they're recombined here, and they look at the interference pattern. So this one is in Hanford, Washington, and this one is in Livingston, Louisiana. And when they simultaneously detect a signal, then you know that you have a gravitational wave. All right, so now here is a picture of the signal as it was detected from the first detection of gravitational waves back in September of 2015. So this is the signal in the Hanford, Washington detector, and this is the signal in the Louisiana detector with the Hanford, Washington one superimposed on this. And these are the signals generated by a simulation of black holes, similar to the one that you saw before, and that matches the signal. So basically, not only did they see a signal, but in fact they were able to verify that this is exactly the signal that you would detect from 2 black holes spiraling in and merging with each other. And furthermore, by matching to the particular black hole masses that generate the right signal, they were able to tell not only that 2 black holes had merged, but what each of the masses of the individual black holes were. Okay, so gravitational wave detection is a great triumph, and as Professor Adams said, it's one that was awarded this year's Nobel Prize. However, it turns out that there is something missing from both the computer simulation and the signal, and that something missing is gravitational wave memory. And I'm going to spend the rest of the talk telling you about what this memory is. Okay, so what's missing? Well, it turns out that each of these quantities, the signal and the numerical simulation, should have an offset. In other words, the signal starts out at 0, and it goes through these waves up and down. And then in the picture I showed you, the signal returns to 0, but it really isn't supposed to. What the signal is supposed to do is to return to a number that's maybe about 5 to 10% of what the peak signal is, the maximum signal. And so in other words, going back to these diagrams, right, we start out at 0, it looks like we return to 0, but we're really supposed to return to about 0.05 to 0.1. And similarly here in the numerical simulations, we start out at 0, we return to 0, but we should really return to some non-zero value. Okay, so what's going on? Well, it turns out that both the signal that's being presented here and the numerical simulation have been cleaned up a little bit. And part of that cleaning has removed this memory, right? So it's not that it's not there or that somebody made a mistake. It's that for purposes of presentation, what you're seeing here is not quite the raw signal. Okay, so let me explain, first of all, in terms of the signal itself, why they're not presenting the raw signal. And then let me explain in terms of the simulation why they're not presenting the whole story either. So the idea is that because LIGO is looking for such a tiny signal, they have to worry about all sorts of noise, all sorts of things in the apparatus that interfere with the signal. And in particular, at low frequencies, there are sources of noise that become quite large as the frequency gets very low. One such source is seismic noise, which basically just has to do with the shaking of the Earth. Now, they go through a great deal of trouble to get rid of seismic noise. That is to say, if they simply had mirrors mounted on a bench the way this interferometer does, there would be an enormous amount of seismic noise. And so instead, what they do is they hang their mirrors from multiple wires and pendulums, which do their best to isolate the mirrors from any shaking of the ground. That isolation is very, very good and very sophisticated, but it's not perfect. So there's still low-frequency noise in the detector. In addition, because the detector is at room temperature rather than at absolute zero, there's a certain amount of shaking that just has to do with fluctuations that do with vibrations of things at non-zero temperature. So there's minuscule, minute shaking of the apparatus, and that shaking gets worse as the frequencies get low. So this signal that's being presented is not the raw signal of the detector, but rather the signal of the detector with all the low-frequency stuff cut out of it. And because of that, they cut out the memory part as well. Similarly, in the simulations, it turns out that as I'll explain in a little bit more detail later, the simulations don't calculate the signal directly. They calculate another quantity and then infer the signal. And it's tricky to do that accurately and get the offset right. And so what they do is they just set the offset to 0 because, well, the detectors are doing that anyway, and we're going to match them, so we don't need to worry about that. So there's something missing from both the signal and the simulations, and this something that's missing is called gravitational wave memory. Okay, so as I said, the offset in the signal is set to 0 because we have to take out the low frequency noise because it's too large, and the offset in the simulations is removed because it's tricky to calculate accurately. Okay, so now I want to come to the sort of paradoxical flavor of this result, right? So what are we saying when we say that there's a gravitational wave memory? So a gravitational wave comes by, and what it does as it stretches space in this direction while squeezing it in that direction. And then because it's an oscillation going back and forth, it next stretches space in this direction while it's squeezing it in that direction. So space gets alternately stretched and squeezed, and then the wave passes, and you would think that what's going on is that space would return to its old unstretched, unsqueezed state. But when I tell you that there's a gravitational wave memory, what I'm telling you is space doesn't do that. Even after the wave has passed, there's a residual stretch and squeeze of space that's still left. So that sounds crazy, right? Gravitational waves just are this stretching and squeezing of space. So after the wave is gone, how can it be that space is still stretched and squeezed? All right, so to explain that, I want to, again, push this analogy between electromagnetic waves and gravitational waves. And I want to talk about something called electromagnetic memory. So it's basically something that has the character of gravitational wave memory, but is just a property of plain old ordinary radio waves. So let's think about what's going on in this apparatus where we make radio waves here and we detect them here. The radio waves are just waves of electric and magnetic field. And if I imagine I have a test charged particle, a small charged particle right here, when that wave comes by, what it's going to do is it's going to move the charge, right? Electric fields accelerate electric charges, and so as the radio wave comes by, the electric charge is going to be moved back and forth like this. After the wave has passed, there will be no more electric and magnetic field, so the charge won't be accelerated anymore, but it could still keep moving. That is, the cumulative effect of all the acceleration of the charge made by the electric field could give the charge a kick. After the wave has passed, the charge could keep moving. So this is the electromagnetic analog of gravitational wave memory, right? Even after the wave has passed, there's still a residual effect. And in the electromagnetic case, that residual effect is a kick of the particle. Now, it turns out that this apparatus will not give such an electromagnetic kick. And the reason is that the only sources of electromagnetic waves that can give an electromagnetic memory are ones where the charges from the source keep moving even after we're done making the waves. Because this antenna has a finite size, that means that when the wave is done from the transmitter, the charges in the transmitting antennas will stop moving. And so that is not something that can give rise to an electromagnetic memory. But if I were to replace these antenna wires by very, very long wires so that the current could keep moving, or if I were to replace this radio transmitter by a particle accelerator that could shoot charges out in both directions, then that would be a source where its charges keep on moving, and that's a source that could give rise to the electromagnetic memory. Okay, so basically, gravitational wave memory works the same way. The gravitational wave is going to stretch space and squeeze space, and it's going to be made by moving objects. And so as long as the source of gravitational waves is something that's going to keep moving even after the whole process is done, it will give rise to this gravitational wave memory where there's a residual stretch and squeeze of space. Now, many years ago, Zeldovich and Polnareff calculated this effect for the scattering of particles because they figured, well, if I want things to keep moving, then I had better consider a system where these two particles under their own gravity just change their position and then just scatter from each other. And you get a little bit of memory from that. And in the ordinary merger of black holes, you get a little bit of the Zeldovich-type memory from the fact that there's a little recoil. The black hole that's formed in the end gets a slight kick from the fact that it's emitted gravitational waves more in one direction than the other. But these are small effects. So when Zeldovich calculated this stuff, people thought, okay, well, this is really too small to bother with. We don't have to worry about. But it turned out that Zeldovich and Polnareff were missing something very important. And they were missing the fact that the gravitational waves themselves have energy that contributes to gravitational wave memory. So when these two black holes or two neutron stars emit a burst of gravitational waves, those gravitational waves are themselves things that are energy and things that are sources for gravitational waves. This is part of the sort of nonlinear property of general relativity. And a lot more energy comes out in gravitational waves than comes from the recoil of the merged object. And so this Christodoulou effect, Christodoulou noticed that these gravitational wave energies would contribute to memory. This is a much, much stronger effect. And this is the thing that makes memory something that can possibly be detected. Okay, so now I want to return to this, possibly paradoxical, how can there be a stretch and squeeze even after the wave has passed? And the way to think about this is to think not so much in terms of the stretching and squeezing of space, but to think in terms of the tidal force, also known as the space-time curvature. So remember, for the electromagnetic memory, that even though the electric field is zero after the wave has passed, that it still has a residual effect in terms of the kick that it gives to an electric charge. Similarly, it's better to think of gravitational waves not as waves of stretching and squeezing, but as waves of tidal force. So I want to start by explaining to you what tidal force is, and then from that, we'll get a better idea of what gravitational waves are like and about how they can have memory. Okay, so this is a diagram with the scale much exaggerated of the effect of the moon and its gravitational field on the Earth. So the idea is, this is the moon over here, and this is a whole bunch of parts of the Earth. Here's the center of the Earth, the surface of the Earth closest to the moon, the surface of the Earth furthest away from the moon, and this stuff on the side. Now, remember that the gravitational field of an object always points towards its center. So what that means is that the direction of the force the moon exerts on the center of the Earth is slightly different from the direction that it exerts on something this side of the Earth, and slightly different from the direction it exerts on this side of the Earth. Similarly, because gravitational fields get larger when you're closer to the object, that means the moon exerts a bigger gravitational pull on this near part of the Earth than it does on the far part of the Earth. Now, the key to understanding this diagram is to think of all of this stuff relative to the center of the Earth. So if this is the amount of force that the center of the Earth gets, then this part gets more, and so it gets pulled toward the moon. This part gets less force in this direction, but relative to the center of the Earth, that means it's actually being pulled in the opposite direction. This part gets about the same force as the center, but because it's at a slightly different direction, it has an extra component that's inward. So the net effect is that relative to the center of the Earth gets squeezed in the directions transverse, and it gets stretched in the directions along the moon. Okay, so this is the sort of thing that causes tides, which is why it's referred to as a tidal force. So if I think of the effect on the oceans of the Earth, then because the Earth is stretched both in this direction and this direction, here and here there will be high tides, and because the Earth is squeezed in this direction and that direction, that means here and here there will be low tides. Okay, so non-uniform gravitational fields can be thought of as tidal forces. They do stretching and squeezing, and that stretching and squeezing is a function both of how big the gravitational field is and also the separation between the points that are getting stretched and squeezed. So the tides are appreciable not just because the moon it has a fairly strong gravitational field, but also because there's a big distance between this near part of the Earth and the far part of the Earth, and over that big distance, that small change in force can give rise to a large effect. Okay, so now let's think about the tidal force of gravitational waves. So a gravitational wave, thought of as a wave of tidal force, comes in and it accelerates the mirrors of the interferometer. So you want to think of the gravitational wave coming by, and its oscillating tidal force makes these mirrors oscillate back and forth. And so once the wave has passed, the tidal force is not there anymore to oscillate things, But the residual stretch and squeeze, the result of the cumulative effect of all that oscillating tidal force, that's still there. So there can be a residual stretch and squeeze, just because even though there's no tidal force anymore, nonetheless, the residual effect of all that tidal force has had an effect. Okay, so now I want to turn to a slightly more complicated, well, a slight complication of this phenomenon, namely the fact that we live in an expanding universe. So the idea is that these objects, the merging black holes and the merging neutron stars that have been detected, these are so far away that we have to take into account the fact that we live in a universe that's expanding, and that in particular, the expansion of the universe between the time those gravitational waves were emitted and the time we detect them is going to have an effect. Now, it turns out that you can calculate this, and one effect is that the stretching of space due to the expansion of the universe will change the frequency of the gravitational waves. But it turns out that it will also change the amplitude of the memory. In addition, our expanding universe is not completely uniform. Rather, there are some concentrations of mass in some places, and those concentrations of mass will give rise to what's called gravitational lensing. So they will bend the signal a little bit, and in some cases can magnify it, and this also has an effect on the memory. So the usual simple calculations of how big is the memory have to be modified slightly to take into account the effect of the expanding universe. Okay, finally, since gravitational waves have been detected, and that's very exciting, but gravitational wave memory, a much smaller signal, has not yet been detected, I want to say a little bit about what are the prospects for detecting gravitational wave memory. So one of the things that you might worry about is that gravitational wave memory is a sort of low frequency component of the signal, because here you're just talking about the difference between what you started with at the beginning and what you're ending up with at the end. And as I've told you, there's lots of noise in the detectors at low frequencies. And so you might worry, well, these detectors are just going to be too noisy, and we're just never going to be able to detect this thing. But it turns out that gravitational wave memory is not inherently low frequency, because even though it's true that there's an offset, that offset will come about with a certain amount of rise time. In other words, the overall offset in the signal will happen at a certain rate. And it's really the rate at which that offset comes in that's the effective frequency of the gravitational wave memory. And while that's fairly small, it's not too small to be overrun by the noise of the detector. So it's not so much noise that makes it difficult to detect. It's really that gravitational wave memory is only one aspect of a very complicated signal. So the idea here is the following. Because the gravitational wave signal is so weak, the detectors find it by using a technique called matched filtering. That is, they take the whole signal from beginning to end, and they take one of these computer simulations from beginning to end, and they look for a match between the whole signal and the whole computer simulation. And what that means is, if you think back to the movie, where we have lots and lots of oscillations, that a lot of the detection comes just from the fact that we have many, many cycles of signal and simulation, and we get to match the two to each other. Similar things come with what's called the detection of quasi-normal modes. So let me just say a few words about that, because it'll help focus us on the, why is it hard to detect this stuff. So one of the predictions of general relativity is that black holes, when disturbed, will ring with a particular frequency and a particular decay time of that frequency. In other words, there's a definite prediction for when the two black holes merge, what this last burst of radiation from the merged black hole will look like. And so one of the things that you might ask is, well, you know, do we have a detection of gravitational waves, so have we detected the quasi-normal modes and verified that black hole event horizons work the way general relativity says they do? And the answer is that we haven't, because these black hole quasi-normal modes are only one small part of the signal. And you need either a very strong signal or lots and lots of detections to verify that this particular part of the signal is there. So quasi-normal modes are an important part of the predictions of general relativity for gravitational waves that have not yet been detected, but that will be detected once we get enough black holes merging that we can say, okay, we're sure this part of the signal is there. Similarly, with gravitational wave memory, all we need is enough systems. If you have enough systems, then you can verify that this particular part of the signal is here, and then you can say that you've detected it. Okay, so with enough detections, LIGO will eventually detect gravitational wave memory. And in particular, they are going to be upgrading the detector so that they can get their rates much bigger. At this point, they have rates of maybe a couple of detections a year. With the upgrades, they may get to a couple of detections a month, and eventually that should be enough to find memory. In addition, there are other types of detections of gravitational waves. There is a proposal to build a giant laser interferometer in space called LISA, and this has much more sensitivity at low frequencies. And there are also an ongoing effort to use observations of pulsars to detect gravitational waves, and this is also much more sensitive at lower frequencies. So eventually with LIGO, and also probably with LISA and with pulsar timing, we expect that the memory part of the gravitational wave signal will be detected. Okay, so to conclude, I want to just sort of emphasize a couple of punchlines of the talk. So the main thing is that not only for gravitational wave memory, but for lots of aspects of gravitational waves, it's helpful to think in analogy with radio waves. And when you do that, you find that gravitational waves are a lot simpler and more intuitive than you might have guessed. Finally, instead of thinking of gravitational waves as stretch and squeeze of space, for many purposes, but especially for understanding memory, it's helpful to think of gravitational waves as oscillating tidal forces. And in that way, even when the tidal force is gone, there can still be a residual effect. And then finally, after enough detections, we look forward to the eventual detection of gravitational wave memory. Okay, so that's it. Thank you.